We're going to go ahead and take a look at applied problems. For an applied problem, you want to read it and probably reread it multiple times until you kind of have a general idea of what's going on. Not necessarily how to work out the problem, but just so that you can understand what's the whole situation is and what they're trying to have you do. You typically want to let your variable represent what you're looking for. That doesn't always work, but it works a lot. If it's a situation where you can draw yourself a picture or a diagram, I would encourage you to do so. Some problems, it's going to be useful to make yourself a chart. Then from that chart or from the problem, you'll write an equation, then you solve it, and then you just have to make sure you check your work and actually answer the question that's being asked. So don't just go ahead and solve the equation and stop. So go ahead and pause the video while you read this problem multiple times. Now, we're trying to look for how much they can spend in the meal. I'm going to let my variable represent what it is I'm looking for, which is, in this case, the cost of my meal. So I'm going to use M. M has meaning in the context of this problem for meals, so it makes it easier for me to know what it is I'm dealing with. Now, the total amount they spend is really made up of three parts. It's made up of the meal, the tax, and the tip. This is our basic equation that we're going to use. All we have to do now is fill stuff in. We know our total is $70. We know our meal price, we're saying, is M. Then we have to add in our tax. Our tax is just 6% of that meal. So you got to take 6% as a decimal, multiply it by your price of the meal, which is M. Now your tip is 15% after the tax has been added. So it's 15% after the tax has been added to your meal. So it's 15% of your tax and meal together. Well, this right here is your tax and meal together. So it's 15% of that tax and meal, which is that M plus 0.06 M. Well, now this is our equation. All we have to do is solve it and then make sure we're answering the question. So we'll go ahead, distribute our 0.15 through. Now we have lots of like terms, 1m plus 0.06m plus 0.15m plus 0.009m. We add those together, we get this. We divide to get m totally by itself, and we get this. So now we got to answer the question, what's the most they can spend? Well, it happens to be $57.42. Pause the video, read through this multiple times. So this one is really just a yes/no problem. However, you need to be able to work out this with math and have it supported with math other than just having a yes or no. So with all these types of problems, when you get to your test, you'll need to go ahead and have the algebraic equations and the correct work with solving those to support your answers. Now, there's two things we don't know. We don't know the price of the bonds, and we don't know how much we're putting in with the insurance company. However, it's a total of 800 million. Well, if we let B be the bonds, what we put in for the insurance company is just what's left over. So it would be our 800 minus what we use for the bonds, or 800 minus B. Now, in financing this, our total amount that we're financing is really broke up in between two chunks. What we're putting into the bonds and the interest there, plus what we're having to pay the insurance companies in interest. Now, if we work in millions, we don't have to include all those zeros. And you'll notice all the numbers up here were in millions as a label, so that's what I'm going to do down here. We have our total amount that's financed, which is 42 million right here. Then we'll have to set that equal to what we have to pay in our bonds for our interest and what we have to pay the insurance company. Well, when you're figuring out interest, it's always just your interest rate times the amount you put in. We're putting in a B amount, and our interest rate for the bonds is 0.06. It's 6%, but remember you got to change your decimal or change it into a decimal by moving your decimal point 2 spots. So it's 0.06 times your bonds. Your interest you're paying the insurance companies would also be your interest rate as a decimal, so 0.05 times what you're putting in, and so it's 0.05 times that 800 minus B. So now we can go ahead and distribute through to solve this. Collect our like terms on the right-hand side of the B's, and then we solve it. And we get 200 million for our bonds. Then if our insurance company, if B is 200, it'd be 800 minus 200, so it'd be 600 for the insurance company. We now have to realize, does this fit the criteria that it's stated up here? And in this case, it would, because, oh, I forgot a space down here. Sorry about that. Because it fits what was listed up here for the criteria. It says, can it be determined to fit this? Yes, because there's only so much you could put in for the bonds and only so much you could put in for the insurance company. And our numbers fell within those criteria, so the answer would be yes. So pause the video, read through this multiple times, and then we'll work this out. So the basic idea here is we need to end up with a 2% solution. So we're going to mix a little bit of the 10% with a fair amount of the 1% so that we can end up with a 2% solution. So you're starting out with 1%, you add some really concentrated 10% to raise it to a 2% overall. So this is a situation where I would start out with a chart. I would use the formula percent of solution for my first column times, for my second column, amount of solution equals, for my third column, the pure amount. Now, I might just start out with a normal tic-tac-toe chart, and then sometimes you have to add an additional row. But you'll notice, we're going to start out with something, we're going to add something to it to get a final amount. So we need to have 3 rows going across to fill stuff out. So now we can start filling stuff out that we know from our problem. So we're starting out with a 10% solution, and 10% as a decimal is this. And we're adding a 1%, so 1% adding is the middle row going across, 1% as a decimal. And we're ending up with 2%, so that's our final solution. So our percent of solution for the final solution amount is 2%, and as a decimal, it's this here. We also know that we need to end up with 15 milliliters. That's amount of solution. That's what we're ending up with. Now, one of the nice things about these charts is whenever you have 2 of the 3 boxes filled out, you can always get the third box. We can take amount of solution, this, times, according to this here, amount of solution. So percent of solution times amount of solution, multiply across to get our pure amount. And so if we do that, we get this here. Now, we don't know how much of the 10%, we don't know how much of the 1%. So we're going to let our variable represent just one of these boxes. I'm going to choose let my variable be the amount of the 10%. But here I have 2 of the 3 boxes filled out, so I can follow the operations up here of the first box times the second box, and it tells me what to put here. Now, I'm trying to end up with a total of 15%, or not 15%, 15 milliliters. I'm trying to end up with 15 milliliters. I was using a certain amount here, so what's left over would be right here, which would be our 15 minus what we use for the 10%. So now we have 2 of the 3 boxes filled out, so we can take this times this to get the third box. In these types of problems, your equation always comes from the right-hand side. What you start with plus what you add has to be equal to your final amount. Well, what we started out with was our 0.1x. What we are adding is this green right here, the green pure amount, equals our final amount, which is this right here. So this is our basic equation. We can now multiply out on the right, distribute through here, collect our like terms, and when we do that, we end up getting 5/3. So x is 5/3. X, once again, was amount of solution of your 10%. So amount of solution is measured in milliliters. So it would be 5/3 milliliters of the 10%. Then of the 1%, all we have to do is take our x, which was 5/3, plug it in here for the amount of solution of the 1%, and then we can go 15 minus 5/3, and we get our 40/3 milliliters of the 1%. So don't just stop after you solve the equation. Make sure you actually answer what it is they are looking for. So go ahead, read through this problem, and then start the video again. So what we have here is basically if you have two cross-country runners, one starts out from the school running towards town to go to Quick Trip. Another one took more time getting ready, starts 5 minutes later, and then runs after the first person. Since the second person is running faster, how long is it going to take for them to catch the first person? This, once again, is another chart problem. It's a rate times time is equal to distance situation. We only have two situations. We have our first runner and we have our second runner. So the rate of the first runner is 6 miles per hour. Rate of the second runner is 8 miles per hour. We want to know how long it takes the second runner to reach the first runner. So we're wondering, how long does it take, does the second runner actually run? That's what we're looking for. So I'm going to let my variable represent that box. Now, just like in the last problem, 2 of the 3 boxes are filled out. We can follow the operations at the top. Our rate times our time is equal to our distance. We now have an expression for the distance of our first or our second runner. Now, we know that the first runner started out 5 minutes earlier. So they're running an additional 5 minutes compared to our second runner. So we know it's going to, the time of the first person is going to be that time plus that 5 minutes. But we're not going to go plus 5 because that's minutes. And our rate's in miles per hour. So we need to make sure we're using hours here. So you got to think, okay, 5 minutes is how much of an hour? Well, it's 5 out of 60. If you simplify 5 out of 60 down, you get 1 out of 12. So you have 2 of the 3 boxes filled out, so you can multiply across to get your distance of the first runner. Now, they're both starting at the school and both running until they get equal with each other. So they're both running the same distances. When you're dealing with the rate times time equals distance problem, either these two distances are going to be equal, like what we're going to have for this problem, or the two distances will add up to be a different third distance. So they both are running the same distance. So we're going to take the distance of the first runner, set it equal to the distance of the second runner, and then all we have to do is solve that. And so then we get 1/4. Once again, our time is 1/4, and we were dealing with hours, so it's 1/4 of an hour. If you did want to convert it to minutes, you could go 15 minutes. Now, there's also a few other formulas that might be helpful for putting across the top of your chart, and those are given to you down below.